Hello and welcome to Statistical Computing. In this module, we will cover vectors in R. This includes atomic vectors, which are the vectors you're probably used to, and also lists. This module will follow pretty closely Chapter 3 from the second edition of Advanced R by Hadley Wickham, and you can find that easily on the internet. There's a web version available for free. You'll notice that I'm working here in the terminal. I am using a piece of software called Emacs, which is installed on many systems and easy to install on many systems. Right now, I've just used Emacs to open an R script. R script is called, you can see at the bottom of the page here, vectors.r. The nice thing about Emacs is that you can run R commands easily. So if I start an R session, it will pop it up in the right-hand side, or the right panel of the terminal. And I can do things like, with various key combinations, send code from the script over to the terminal. And I can switch back and forth and type it out and look at it. So this is very similar to RStudio, and I imagine many, if not most or all of you, will be using RStudio. I have nothing against RStudio. I think it's a great piece of software, but personally I'm more comfortable using the terminal. There's a whole bunch of stuff I can do quickly with keystrokes in Emacs and switching between terminals and things like that. So I find it most efficient to work in Emacs. By the way, the program within Emacs that I'm using to run R is called Emacs Speaks Statistics, and you can read about that if you like. So again, I imagine most of you are using RStudio. I'm going to use Emacs partly because I want you to just see that this exists, so that maybe if you want to use it as well, you could look into it further and use it. Okay, but this is going to work basically the same as RStudio. There's a script up here, and there's an R console. In this case, I have the R console on the right, and I send commands back and forth, and it prints them out. Okay, so there's nothing kind of too scary here. All right, so let's start with atomic vectors. So the atomic vector is what we would normally think of as a vector in R. So I've already defined the first vector A. So A. So let me go through this step by step. I'm creating a variable called A, and I'm assigning it the vector 1:20. So what the colon does is it takes a sequence of integers between 1 and 20. So you can see on the right, it prints out 1, 2, 3, 4, 5, 6, 7, up to 20. The thing on the right-hand side, so the thing in the middle is called the assignment operator. This is equivalent to doing an equal sign, so this works as well if I were to run that. I prefer to use the assignment operator. We'll say a little bit more about this when we talk about functions. But people use both. But generally, I think good practice is to use the assignment operator, which is less than dash, when assigning values, like this vector 1 through 20, to variables, which is A. Okay, so that does that. This is a vector. You could think of a vector just like you think of a vector in math. It's an ordered list of numbers. But as we'll see in R, there's lots of different types of vectors. Okay, so this is called an atomic vector because each element of the vector is an indivisible R object. So each element of A is a number. So the fifth element of A is 5. And 5 is an object that you can't divide into smaller objects, meaning that 5 itself is not a vector, and you can't extract a subvector of 5. Atomic vectors have the additional property that in R, all of the elements of an atomic vector are the same type. So for example, I couldn't combine, well, we'll see this later. I can't have A can't have both strings and numbers in it. It has to be one or the other. Okay, so to get the type, there's a function in R called type of. By the way, if you want to run functions in R, you type the function name, and then you use round brackets, parentheses, and any arguments to the function go inside the round brackets. We'll look at this in more detail when we talk about functions, but we're going to have to use functions before we get to describing them in detail. So this is how you use the type of function. The argument is an object, and what it returns is a character string. Here it returned the character string integer. That tells us that the atomic type of the vector A is filled with integers. Now, if you want to see what the type of function is doing, you want to get more information about it, we can look at the documentation for the function, and this works for pretty much any function. We'll type question mark and then the function name, and that will pull up documentation. So if we look at this one, all the documentation are going to have a similar format. It's a standardized format. Some of them have additional fields like notes, or we'll see some functions with different fields. All of them will have a description. It's a short description. All of them will have a usage section, which tells us how to use the function. After the usage section, they tell us what the arguments are. So if you see here, they say type of X, and then they tell you what X is. So X is any R object. And then there's a value section. What this does is it tells you what is returned by a function. So every function in R returns something. And the value section tells us what it returns. So this one returns a character string. And it tells us something about the possible return values. So there are logical, integer, double, complex, character, raw, and list. List, null, closer. Okay, so there's a lot of them. We'll say a little bit more about what each of these are. In this module, we're going to talk about logical, integer, double, complex, and character types. A lot of our documentation is going to have a see also section. This is written by the function author, and what there's telling you here is these are some other functions that have documentation that are related to the functions documentation that you were looking at. So this says mode and storage mode and is S4 are functions that are related to the type of function. And then most documentations are going to conclude with an example sections, which gives us specific examples of how the function is used. By the way, if you want to run the example code, most documentation don't have this here, but in general, you can type examples and the function name, and it will run the example. Let's see if that works for type of. Examples, type of. Let's try this. I think it's the example. Okay, that works. So this runs those two examples that were in the documentation, type of 2 and mode 2. All right, so let's look at these types. So the first one is logical. So this encodes true and false values. So if we want to create a vector of logicals, we could do it this way. So we say C, true, false, false, true. We're using the C function. C is short for concatenate. And C is a common function to use for creating vectors. Basically, you use it like this. You say C, so C is a function, so we're going to call it with parentheses. And then we list out, separated by commas, the values that we want to combine together into a vector. So this will combine the 4 values, true, false, false, true, into a vector, and then assign it to the vector B. So if we do that and say type of B, we'll get logical. We've already seen an integer vector, so A is an integer vector. Type of A is an integer. If you define a vector in this way with this colon syntax, it automatically makes it an integer vector. If you want to use C to define an integer vector, there's a special syntax for telling R that you want the type to be in integers, and you add an L to the end. So this defines the integer vector 583. So type of is integer. Now, if you don't append the L, R assumes that it's a double. So this is like non-integer values. So 5 is both an integer, but it's also a real number. So if you do this, you get a double. And of course, if you were to say 5.3 or pi or e, that's going to be a double as well. The next type is complex. Complex isn't used that often, but it can be useful, as I'll show you here, if you're doing something like signal processing. So in math, we represent the number square root of -1 with I. Now, if you try to type I in, R is going to look for a variable called I, and it sees one's not found. So the syntax for the imaginary number I is 1I, and you can see what gets printed out is this complex number format. You have the real part plus the imaginary part. So I is 0 plus 1I. And then you can do definitions. If you look at type of, this should say G. Type of G is complex. And like I said, complex numbers aren't used all that often in statistics. But if you're doing something like signal processing where you're taking Fourier transforms of vectors, you'll get complex back. So what this line does is it creates a vector of random, let me run this, standard normals of length 10. So these are just draws from the standard normal distribution. And then it takes the fast Fourier transform, or I should say it takes the discrete Fourier transform by applying the fast Fourier transform algorithm. And this gives us complex numbers. Okay, so those aren't used too much, but could be useful. The last type we're going to talk about here are character vectors. So these are just strings. So if you want to have a vector with the values hello and there, you define it that way. Again, we're using C, and type of is a character. Now, since R is used for data processing, it also has special types to handle missing values. It also has something called null type, and it has infinite types. So the generic missing value object is called NA. So if we do this and look at A, we get 3.7, NA 7.2. The purpose of NA is to encode missing values. So this is like if you intended to measure 3 lengths and you didn't get a measurement for the second one, you'd put in an NA. There's a null type. So the purpose of null is to be a generic length 0 object. It can serve several purposes, as we'll see. So if you do this and look at B, it just omits the null. There's also a not a number type. So if we try to compute the square root of -1, we get a warning that NaN, which stands for not a number, is produced. And it will put in an NaN. So NaN is different from NA. So NaN is used to indicate like illegal mathematical operations. So even though there's a complex type, R treats square root of -1 as not a number. There's also, 1 over 0 gives inf. There's other things that you could do that will produce NaNs. And that brings us to inf. So inf is a a value in R. If we type E, we get an inf there. One useful thing about infs is you could treat it as some algorithms, they like look for the minimum of something, and so you want to check that the current value is less than the current minimum, and you have to initialize it with something. So often you can initialize that with an inf or a minus inf. Okay, yes, by the way, there's also a minus inf. Okay, so there are functions for detecting missing values, not a number, and there's also something called isFinite. So if you do is.na of a, you'll get false, true, false. Remember, a was 3.7, na 7.2. So this tells us whether each element of the vector a is missing or not, so only the second one is missing. IsNan tells us whether it's not a number, and isFinite checks for nans, nas, or infs. So if we could do is.finite of e, we get true, false, true, because the second one was infinite. So I would recommend looking at the documentation to see exactly what these do. And by the way, my main recommendation for when you're learning R, and this probably goes for learning anything, is that you read through the documentation carefully. You're going to run into situations where you don't know how to do something, or maybe you know what function to use but not how to use it. As you're learning, it's almost always worth it to take the time and read slowly, carefully through the documentation. You'll almost always learn something. And honestly, I almost always learn something. I've been doing this for many years, and I almost always learn something when I sit and read carefully through the documentation. In the long run, that's a much more efficient strategy than just Googling things and learning the minimum of what you need to know to get past the task. So take the time and read documentation. And this is a good example to see what these do. Okay, so like I mentioned above, atomic vectors are not only indivisible, they also must have the same type. So the way R handles this is if you try to combine elements of different types, R will automatically coerce them to a higher type. So what does higher type means? There's a ordering to these types we've talked about in R. And the most basic type is logical, then integer, then double, then complex, then character. And the way this works is there's always kind of a mapping to go to the higher type, but not always a unique mapping to go to lower types. So R will always coerce to the higher type. So let's look at some examples. So if I just make length 1 vector A, which is true, I do type of, it's logical. And then if I try to append an integer to A, we'll see what happens. So R is going to see that A is type logical, and the next element is type integer, and it has to do an automatic coercion, and it converts both of them to integer. So the conversion of true to an integer is a 1, and we can rerun this with false. The conversion of false to an integer is 0. So that's useful for doing operations on sums of trues and false to know that. All right, so type of B is integer. Now if I want to add, let me rerun this. If I want to take B and append to it the number 1, remember R will treat this as a double because we're not putting the L on it. Nothing really changed. The output, the display doesn't really change, but if I look at the type, it's now a double vector. If I append the imaginary number 0 plus 1i, then the display changes, and that indicates that it's changed to complex, and we can confirm that by doing type of. All right, and then if I append a character vector, so the string square root of -1, and I look at that, now you can see that R is interpreting all of them as characters, and it has a conversion. Basically, it puts quotes around whatever was in the other elements of E. And the type is, of course, a character. All right, so a few notes. Automatic coercion is a common source of silent bugs. So you'll notice when R was doing all these conversions, it didn't tell us that it was converting anything. So this can happen a lot when you're writing code. You have a big complicated script, and inadvertently you're appending a character vector to a numeric double vector, and your code runs, but it's giving you weird output. It could be because of that automatic coercion. All right, another thing is R does not distinguish between a scalar and a length 1 vector. So in R, there are no scalars. Everything is a vector. The other thing is C. This is important because it kind of explains how C is getting used here. So what C does is it appends vectors to each other. So, for example, in this line here, it's appending the vector B to the length 1 vector 1. So that's why that works. For distinguishing characters, strings, and R, you can either use single quotes or double quotes. So single quotes works just as well. I'm going to use almost always double quotes, but you could use single quotes. And I think just looking at code examples I see, most people use double quotes. So that's what I do. So coercion can be really useful. It's a bit dangerous because it doesn't always tell you what's happening. Some functions will do the coercion for you automatically. So if you look at this line, we're creating a length 3 vector, true, false, false. And if we try to add these up, what the sum function does is it coerces true, false, false to 1, 0, 0 and adds up those values. So you should get 1. And mean does the same thing. So if you take the mean of 1, 0, 0, you'll get 1/3. And there's a lot of functions do this. Another example is nchar. So what nchar does is it counts the number of characters in each element of a vector. So actually, let's print this out first. So this creates that vector. And if we do nchar, it's going to convert it to a string. And let's see what it did. So it converted 1.23 to the string 1.23, which has 4 characters. Converted 12 to the string 12, 2 characters. And then pi and e, it converted to length 16 characters. So these functions are doing it automatically. If you want to have more control, it's probably a good idea to explicitly do the conversion yourself. So if we do as.integer, it does that. As.character does that. You can see exactly what it did in the nchar function. You can convert integers to doubles and doubles to complex, so on and so forth. So these as functions are really useful for giving you manual control for these coercion operations. So I would use these in your code to sort of not give R the discretion to decide when it's going to do coercion, for you to do it explicitly so that others reading your code can know exactly what's going on. Okay, now there's the as dot functions. There's also kind of a catch-all function called as. And the way it works is you plug in the first argument the vector that you want to convert, and then the type that you want to convert it to. So this line is equivalent to saying as.character of true, false, false. Okay. Vectors and all objects in R can have properties associated with them. So one of the important properties of a vector is its length. So if we create B, so B is the numbers 1 through 10, integers 1 through 10. we can look at the length of B. It's 10. Another important attribute are the names. So what names tells you, it gives you a label for each element of the vector. So let's look at A. What was A? All right, so A is true. Actually, let's redefine A. Let's say A equals 1 to 3. So A is 1 to 3. Names of A is null. So we haven't given names. So there's A. We haven't given names to the elements. But we can use the names function to assign names. So if we say names A, assignment Bill, Susan, Jamie. Now when you print out A, it has names associated with each entry. So this is our first example of something called a replacement function. So this is syntax, if you probably didn't think about it too much, but this is a little bit weird that on the left side of the assignment operator, we have a call to a function. So normally the call to the function will go to the right side of the assignment operator. Like for here, we're calling the function C and we're assigning it to something. But here we have a function call on the left side, and this is a special type of function that allows you to assign a value to the names property of A. So when we do this, then we changed A and given it names. Another way of assigning names is explicitly when the vector is defined. So in the C function, you can give the names like this. So Bill equals 3.5, Susan equals 9, Jamie equals 10. And then print out B, we get this. We can extract, and then we'll extract the names with the names function. So this function names, it serves kind of two purposes. One is to extract the names of the object B, and the other is to set the names of the object inside. So let's look at the documentation, because that's a little bit new for us. So question mark names. Okay. So the description is functions to get or set the names of an object. And then you can see the usage here is names X and names X assigned to value. So this is our first example of what's called a replacement function. And in the documentation, it will tell you whether it's a replacement function by having this kind of syntax. So this also works for length. So if we look at B, it's a length 3 vector. If we set the length to 7, what it's going to do is append 4 NAs to the end. So these vectors are kind of flexible that if you, there's this length attribute. If you change the length attribute to make it larger, it will just add missing values to the end. If we want to remove the names, there's a function called unname, and as.vector removes them as well. Okay. Now, as kind of a practice yourself exercise, read the documentation for as.vector and is.vector. All right, so I talked a little bit before about the difference between the two assignment operators, arrow versus equals. I think it's good practice to use arrow when assigning. One of the reasons is the following. So equals are used for named function arguments. So in this example, C, we're giving C 3 arguments and we're naming the arguments Bill, Susan, and Jamie. So this works just fine. If we look at B, it did what we thought it was supposed to do. I like this better because it distinguishes between two different types of assignment. So here we're assigning kind of temporary values to these arguments to the C function, whereas this is a more permanent operation. You can use the more permanent operation in as in the arguments. So if you can't, this actually works. So we're doing Jamie assigned to 0 in the C function. If we print this out, it didn't assign a name to Jamie. It doesn't assign anything to Bill. So Bill's a not found object. Neither is Susan. But Jamie was assigned to 0. So this is probably, you probably never use the C function this way. And I don't recommend using it this way. I'm only showing you this because conceptually I prefer to use this assignment operator because it allows me to distinguish between an operator that's used to assign values to variables that are available to us and to assign arguments, named arguments to a function. So for that that's one of the reasons I prefer to use less than dash for assignment. Okay, so that was a bit of a digression. Let's get back to different attributes. For matrices, one of the important attributes are its dimensions. So let's make a vector. So here's a regular old vector. Its length is 8. And if we try to look at the dimensions of it, it's null. So that's telling us that A is a vector, but it's not a matrix because it doesn't have dimensions. A matrix is simply a vector with a dim attribute. So that's kind of important to remember, and this will come up in the next module when we're talking about indexing. So if all I do is I set the dim attribute of A to be the vector 4, 2, basically I'm saying I want this to be a matrix with 4 rows and 2 columns. I can print that out. And then if I print out A itself, R recognizes that A has a dim attribute and it treats it as a matrix and prints it out accordingly. So it's printing it out as a 4 by 2 matrix. We can change the dimensions. So here's an 8 by 1 matrix. And you can see that this is a column vector, and R is distinguishing between just a plain old vector and a column vector because the printing is different. We can unset the dimensions using the null. This is one of the uses of null. Basically, it's deleting this dim attribute. And then we look at A, and now it's back to a regular vector. Okay. One note I hear, when these values get input, so when I do 4, 2 and print out A, the order that the vector 1 through 8 gets input into this matrix is it loops over the rows within a column. So it starts in the first column, goes 1, 2, 3, 4. Once that column's finished, it takes the next value, 5, and starts the second column with it. This is called column major ordering. And that's just how it works. The other way of doing it would be row major ordering, which would go 1, 2, 3, 4, 5, 6, 7, 8. So by default, R does column major ordering. We'll see this. There's another function called matrix, which allows us to define a matrix directly instead of in one step, instead of 2 steps through setting a vector and then setting dim. So this is usually how matrices get defined in R. So if we do this and print out M, it's going to fill in a matrix with the values 1 through 8, a 4 by 2 matrix, and it's going to do it in column major order. If we want to do it in row matrix order, we set by row to true, and you can see that does the other way. Matrices can have names associated with them, specifically column names and row names. So when we set this with the colnames function, so colnames is an attribute of a matrix, and we can, let's see, if we print it out, we see the column names. Colnames works just like names in that we can extract the values by running the function, or we can also use it as an assignment. Row names works exactly the same way. So here we've defined the column names to be column 1 and column 2, and the row names to be R1, R2, R3, R4. Another important attribute in R is an object's class. So if we run class of M, it tells us that M is a matrix and an array. We'll talk a little bit more about arrays later on in this module. Actually, right away. A matrix is simply a two-dimensional array, and you can have higher dimensional arrays. So let's look at M. M is this object, the 4x2 matrix. If we set the dimensions to be a length 3 vector, meaning there's 3 dimensions, and each is dimension 2, we could do this. And if we print this out, now R is recognizing that we want this to be a 3-dimensional object. And the way it gets ordered is columns, let's see, columns, then rows, then slices of the array. So it takes the first slice, goes 1, 2 in the first column, 3, 4 in the second column, and then the second slice, 5, 6 in the first column, and 7, 8 in the second column. If we look at the class of M, it's an array. It's no longer a matrix. A matrix is specifically a two-dimensional array. We can convert it. We've already looked at a couple ways of converting things to vectors. One of the ways of doing it is to say C of M. So basically, if you do this, it strips the dim attribute and converts it back to a vector. And here it recognizes that it's an integer vector. All right, so we'll say more about classes later on. This is an important thing for object-oriented programming. For now, you can just think of it, I want to get some information about this object. I'm going to look at class. By the way, there are other ways to get information. So one of them is str. You'll see this in the textbook. This prints out information. So this tells me it's a three-dimensional array. The dimensions are 2 in each, and it's filled with integers. Okay. A really important topic to understand in R is that of recycling. Many R objects and functions use the concept of recycling. And this is another source of silent bugs. So let's see how this works. So what we're trying to do in this call here is we want to define a matrix with the values 1, 2, and 3. But we want it to be a 3x4 matrix. So the second argument is the number of rows. The third argument is the number of columns. So this is kind of an issue because a 3x4 matrix has 12 entries. And we're only giving it 3 entries. So if we run this, let's see what happens. It works. So what did R do? It took the numbers 1, 2, 3, started in the first column, and filled them out. And then it got to the next entry, which is here. It realized it had run out of elements of the vector you supplied it, and it just started back over at the beginning. So it does 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So this is called recycling. It's a useful thing, but it's also, like I said, a source of bugs. So here, where we want 4 rows and 3 columns, what it did is 1, 2, 3, then it got to here, started over with 1, 2, 3, 1, 2, 3, 1, 2, 3. Now, if you try to do other things, so here we're giving it the values 1 through 5. So we're trying to fill an object, a matrix that has 12 entries with 5 entries. Now, R is smart enough to say, I'm guessing this isn't what this person intended to do, because the number of elements of this matrix is not a multiple of the number of elements you supplied to it. So 12 is not a multiple of 5. And when it does that, it prints out a warning message. Data length 5 is not a submultiple or multiple of the number of rows. So R kind of detects that you didn't intend to do that, and it prints a warning. But if it is a multiple, it doesn't print a warning. So you may also, in these cases, have not intended to do this, but you did it anyway, and R is not telling you did that. So this could be a sort of what people call silent bugs. one of the main useful things about recycling is if you want to initialize a matrix with a default value. So here we're giving it the default value NA. And like I said before, this is a length 1 vector. So what R is going to do, it has this length 1 vector and it's trying to fill in 12 entries of this matrix. It's just going to recycle that length 1 vector over and over again. So that's what this does. Okay. So in the lab and exercises, we're going to look at some special types of vectors. So a matrix you can think of as a special type of vector with a dim attribute. There are other special types, namely in the lab, we're going to look at factors. And in the exercise, we're going to look at dates and date times. Now I want to finish off here. So these are attributes that have functions associated with them. You can also set, there are other attributes that don't have functions associated with them, and you can also set custom attributes. So let's make this matrix M and look at its attributes. You can see it has a dim attribute. Notice it doesn't print out the length, like you can do length of M, and it has a length, but it doesn't print them out in attributes. So it prints out some of them, but not others. If you want to get or set attributes, you can do it with the attr function. So if I look at att, so the syntax is attr object that you want to look for attributes for, and the second argument is which attribute. So this returns the dimensions 4, 2. You can also set attributes. So let's do this, attrm dim assigned, let's say, make it a row vector, and then print out M. You can set them with the attr function, just like with the dim function. And then, so dim is an attribute that R knows about and knows what to do with. You can also set your own custom attributes. So these are just some silly examples. If we wanted to assign a color, so color is not an attribute that R knows anything about, but we can set it. The matrix has a weight, you can set that. And then when we print out the attributes, it will give us that information. So you can think of this as metadata. It's kind of data about the data. And this can be really useful in some situations. Some R programmers make heavy use of attributes. Some R programmers don't use them much at all. I'm a person who doesn't use them much at all. But you should know they exist because some people use them. And you might find them useful as well. So that's all we'll say for now about atomic vectors. The other type of vector in R is called a list. So basically a list is a non-atomic vector. And the way a list works is that each element of the list is an R object, and there's really no restrictions about what type of object you put in the list elements. So let's look at an example here. So let's look at the matrix M, and let's set the call names and the row names and print it out. Now if I wanted to extract both the column names and the row names, you could do that with the dim names function. But if you think about what would have to get returned, it's going to return a vector of length 2, and which are the column names, and a vector of length 4, which are the row names. And there's not really a natural way to combine those into an atomic R object, a single vector of. It wouldn't really make sense to put them in a vector of length 6, because then the user has no way to really distinguish between where the row names start and end and where the column names start and end. So what R does is if you extract the dim names, the names of the dimensions of M, it puts them in a list. So you'll know you're looking at a list when you have this kind of output here. Basically, there's this double bracket thing here, and what it's saying is that it's a list of length 2. So there's two of these double brackets, 1 and 2. And the first element of the list is the vector R1, R2, R3, R4. And the second element of the list is the vector column 1, column 2. We'll talk more in the next module about these double brackets versus single brackets. No cliffhangers. The idea is that you can use single brackets to extract elements of atomic vectors and use double brackets to extract elements of list. So I'm not trying to hide anything, but we'll talk about that more in the next module. Okay, so the list is a natural object to store something like dim names because the elements of dim names are kind of two different types of objects. They're vectors of different lengths. And so an atomic vector isn't really the right way to do it. Okay, so if you want to define your own list, you do it with the list function as one way to do it. You can think of the list function as the analog to C. So you can give it as many arguments as you want, separated by commas. And the things that you separate by commas are the list elements. So let's look at each of these individually. You can probably guess what 1 to 4 does. Letters is an object in R which holds the letters. So letters 1 through 10 is A through J. This, we'll talk more about functions later, but this just defines a function. And then this is a null object. So if we run this, we define a list called A. If we print it out, prints out just like dim names did. You can see it has 4 elements. The first is 1 through 4, the second is A through J, the third is a function, and the fourth is the null. So already you can see one minor difference between list and C. If you did C, 1, 2, 3, null, it ignores the null, but list does not. So that's one difference. The type is a list. So remember, for atomic vectors, type of returns the type of the elements of the vector. Now, if you do type of a list, there's no requirement that the elements of the list have to all be the same type. So it doesn't really tell you much. It just says this is a list. Class gives the same thing. Just like atomic vectors, you can name the elements of the list. So here I'm just saying my numbers, some letters, fun. So this is going to be a list of length 3. If you print it out, instead of using the double bracket, it gives you the names of the elements of the list. And then the syntax for extracting them, again, no cliffhangers here, but we're going to talk more about this. So A1 is 1 through 4, but you can also get it with A my numbers, A $ my numbers. Okay. Names function works on lists just like it works for atomic vectors. If you can rename things with the names function. And then, of course, you can extract the names as well. People sometimes refer to a list as a nested data structure. Reason is because the elements of the list can be basically anything. And so an element of the list can be a list itself. So it's sometimes called nested or hierarchical data structure. So if we say, I want to create a list where the first element is A, which happens to be a list that we defined above, and then the second element is a sequence of 10 random numbers. So if we print that out, you can see the hierarchical structure at work. So this one refers to the first element of B. This 2 refers to the second element of B. And then this 1 refers to the first element of the first element of B. This is the second element. This is the third element. Okay. Now, somewhere between atomic vectors and lists are where data frames live. So we can think of a data frame as a special type of list. So remember, a list can be an object whose elements are pretty much anything. A data frame is a special type of list. And the way it works is that each list element has to be a vector of the same length. So let's see this in action. So I'm going to create the vectors A, B, and C. Let's print them out. A, B, C. Oh, sorry. A, B, D. Oh, that reminds me. I didn't define an object called C. I'm skipping it. You can define an object called C, but it can create confusion because you can see when I printed out C, it treated C as a function. And remember, C is the concatenate function. So I try to avoid assigning values to the variable C. Another one is lowercase t, which is the transpose operator for matrices. Okay, so we have these three things, A, B, and D. And I want to create a data frame with those objects. So let's just look at it. So the function is data.frame. So this is kind of the analog to C or to list for data frames. And if I print it out, I get this. So a data frame is a rectangular object where each column represents a variable and each row, the word people use, is an observation. But the main point is that the columns have to be atomic vectors and they all have to be the same. Well, they have to be vectors. We'll see, they don't have to be atomic vectors. But they have to be vectors and they all have to be the same length. Okay, so in this case, they are atomic vectors, though. You can, just like C and list, you can assign names. So here I want to say the first column are words, the second are real numbers, and the third are complex. You can extract column names and row names. Here are automatically set the row names to 1, 2, and 3. And then you can extract names. So it's kind of interesting. Let's see, if we still have M. If we try to extract the names of M, what do we get? We get null. Okay, so R says M is this two-dimensional object. It's a matrix. Let me remind you. Class M is a matrix. And if I just want names and I don't specify row names or column names, R says, I don't know what you're talking about. Because I don't know if you want row names or you want column names. If I want both, I do dim names. If I want column names, I do col names. For a data frame, if you do names of a data frame, it is, if you think about this, it's treating the data frame as a list. So the list elements are the vectors A, B, and C, named words, reals, and comps. And it's extracting the names of those list elements. If I do the length, it's treating dat as a list with 3 elements, which are the columns of the data frame. If you recall, if we look at M is a matrix, not a data frame. If we look at the length of M, it's going to return 8. So this is a difference between data frames and matrices. If we do type of, this treats it as a list. It really wouldn't make sense to give a type in this case because the different columns can have different types. And the class returns data frames. If you want the number of rows, you do n row. Number of columns, you do n col. Okay. Now, since a matrix is similar in spirit to a data frame, you think of a matrix as a data frame where you're requiring all of the elements to have the same type, not just within a column. So these are similar types of objects. So you can convert a matrix to a data frame. So let's M. And the function is as.dataframe. So what it does, so M, if you print it out, it doesn't have row names or column names. What R does when you call as.dataframe is it gives it some default column names and default row names. The default column names are usually V and then the column number. All right, so last thing I want to talk about here are tibbles. A tibble is a alternative data frame class. Tibble is part of what's called the tidyverse, which is, think of that as like a group of R packages, R software, to try to clean up what are some perceived problems with R. And a lot of people find these really useful. I think the Tibble has some nice properties. All right, so to use a Tibble, so Tibble is not part of the main base R package. It's a separate package. We'll talk more about packages later. But if you want to use the Tibble functions, you can call library Tibble, which will kind of make all of the functions in Tibble and classes available to you. So we do that. Now we can use functions such as Tibble. So let's remind ourselves, this is dat. If we do as underscore Tibble of dat and assign that to tib, print it out. The first thing you notice is that the formatting of the printout is a little bit different. So basically it tells you that tib is a 3x3 Tibble. It gives you the column names, word, reals, and comps. And it tells you something about the type of each column. So the first column, it says CHR to signify its character. Second columns are doubles, and the third column are complex. So that's one immediate obvious difference. You can also define, so the analog to data.frame is Tibble. So you define tib that way, you get the same thing. Another difference in how they're printed out, well, I'll illustrate here. So say you want to create a big data frame that has 4,000 elements. It's a 200 by 20 data frame. So that's that. If you print it out, you get this gigantic printout. I'll scroll up here. So 200, you can see 200 rows. And it printed out all 20 columns. There's a ton of stuff here. Now sometimes you do want to print all this out, but more often than not, you really didn't intend to print out the entire data frame. You just wanted to print it out to kind of give it a quick inspection to see whether it is what it did, see if it did what you thought it did. So that's dat. If we convert it to Tibble and print it out, it's giving you a little bit more complex printout of the data frame. And a lot of people like this, and I like this too. So it tells you again, it's a Tibble, it's 200 by 20. And it prints out the first 10 columns and the first 10 rows of each column. But then it tells you at the bottom that there are 190 more rows, 10 more variables, and it gives you the names of them. So I like this. It's a little bit more compact printout. If you want to have more control over it, you can you could say print tib and alter the width argument. This, if you set it to 100, it prints out all of them. Okay, so Tibble is something to look in. A lot of people use this, and I think it can be useful. There are other differences. One is how it handles row names, and you can read more about that in the chapter. Okay, last thing I want to show you is that the columns of a data frame do not actually have to be atomic vectors. So say I want to create a data frame where each row is a city, and then the columns are the name of the city and the coordinates of a point within the city. So coordinates is it's not a one-dimensional object. It's kind of inherently a latitude and longitude is a two-dimensional thing. So you can make a column where the first column is the city name and the second column is the coordinates. Here we're calling data frame. We're giving it two arguments, city equals, and then comma, and then coordinates equals something. We'll say more about this in a second. And then closing the data frame. By the way, we could do this and put it all on one line, but this is kind of hard to read. So in our syntax, it does allow you to put returns and white spaces. And so it's very useful for you trying to understand your own code and for other people reading your code to try to print things out in a way that is easier to look at. So I find this personally easier to look at. All right, so if we run this, we'll see it works. Let's look at dat. And let's see, dat, we could do dat dollar city, dat dollar coordinates. So coordinates is a list. So the syntax here is we want this to be a list. So list of length 3, each element is the coordinates of the city. It actually doesn't work if you just put in list. You have to surround it in this I function, which you probably recognize from doing linear regressions with like squaring some of the variables. Oops. So that's dat. In this case, this isn't perhaps the best use case because you could define a column that says latitude and a column that's called longitude. But this kind of thing is not well known. It can be useful if, for example, one of the columns is a vector where the length is not the same. So one of the examples that comes up in spatial data analysis is so for example, if each row is a county, and you have things like county name and population, area, things like that. One of the common attributes would be a sequence of points that defines the boundary of the county. And some counties are square, or rectangular, so you can define them by 4 points, but other counties are more complicated and they require many more points to define their boundaries. So in that case, it's useful to be able to have a data frame where one of the columns can be a list. And this is used extensively by the SF package for that particular use case to define points in a polygon. Okay, so that's it for vectors, and we'll see you at the next one.